recording here. Okay, so we're talking about maximum and minimum values of surfaces, and that's section 11.7. And if you recall in calculus, you know, when you had a function, here I'll just draw an axis here. Hold on. Why is that not drawing? Okay, I'm going to just draw a, you know, function. Here we go. And at A, what do you have at A? Is this for this function f of x? That's right, Robin. You have a maximum. You have a maximum there. Okay, and when x equals b, what do you have on the function there at b? Good. You have a minimum. Good, Deodath. Good, Robin. And so how do we find these values of a and b? I mean, what do we need to do to find those maximum minimum values? What do you notice about the tangent lines? Well, second derivative, Eric, deals with concat. Well, okay, I hear what you're saying. Okay, but I want to be a little careful on that. Before I say yes to that. But okay, that's right, Christian. And what to find the critical points? What do you set the first derivative equal to? That's right, 0. So by setting the first derivative equal to 0, and usually in calculus, you know, you had a polynomial or something like that, you would set the first derivative equal to 0, and then you would solve that equation, and you would identify values of x where the slope at those values of x equals 0, you know, flat. So for a maximum or a minimum, I'm not talking at the endpoints now. I'm talking, you know, just like where you see it here. You have to have a tangent line. So the slope of a tangent line equals 0. So all the critical points come from solving this equation, f prime of x equals 0. And then, you know, if you want to determine other things, you can use the second derivative. But of course, now we're not talking about a function of one variable. Now we're talking about a function of two variables. In section 11.7, you're talking about a function of two variables, f of x and y. So on that note, let's go into the book here. And they show here in figure 1, they show, and again, if you click on your screen twice, you'll be able to blow that image up a little bit. You have here a surface, and you have local maxima, local minima, and then you have absolute maxima, absolute minima, just like in calculus 1, but only you're dealing with the surface. So the question then becomes, how do you identify where these local maxima and local minima are? You know, how would you identify this? Well, so you could say, I mean, at the top, if you think about like think about like the maximum. Like look at that, like one of the maximums there. Look at that big maximum there. The tangent lines to the point at the top of the hill. If you have a tangent line going in the x direction and a tangent line going in the y direction, what would the slope be of those tangent lines? So that absolute maximum there in figure 1, if you had the point at the very top where the maximum is, and you pass through two tangent lines to the surface through that point, one going in the x direction, one going in the y direction, what would the slopes be of those two tangent lines? Would the tangent lines be horizontal? Would they be flat? They would. Absolutely they would. That's right, Robin. And you know, we're going to use two tangent lines because critical points consist now of coordinates x and y. And so you need two pieces of information. As a matter of fact, any tangent line drawn in the direction of any vector on the top of a maximum or at the bottom of a minimum on a surface would have a slope of 0, right? But the two easiest tangent lines to work with are the tangent lines that go in the direction of x and the direction of the x-axis and the direction of the y-axis, you know, in the direction of the I vector and the j vector. And so we utilize that idea, and we come up then with how to find a critical point. So hold on here. Yeah, let me see. Hold on one moment. There was a box I was looking for. Yeah, Fermat's theorem. Fermat's theorem. Okay, if you have a local maxima or minima, this is right here, Fermat's theorem. If you have a local maxima or minima at a point AB and the first order partial derivatives exist there, then those partial derivatives both have to equal 0. And so this is how you establish what your critical points are. Now, the next thing you have to establish is, once you identify the critical points, are the critical points maxima or minima? Are the critical points maxima or minima? And for that, we have a test called the second derivatives test, okay, which is right here. Okay, this is the second derivatives test, and it's actually proven in the appendix. But to determine whether you have local maxima or local minima, you evaluate this quantity d, which is the product of two second partial derivatives, f sub xx, f sub yy, minus the square of the mixed partial derivative. And then based on the value of d and based on the value of your second partial derivative of x with respect to x, you can establish whether you have local maxima or local minima. So this is a test that's done. And you know, now with like software, there are programs that will find you the maximum and the minimum of a surface, okay, numerically. But this is an analytical way to find it. But of course, if we deal with nice surfaces that are easy to work with, this is easy enough to apply. So I just want to look at this at an example of a second derivatives test here. And I might be just run a few minutes over, but it won't be long. If you can, it'll be on the recording. If you can stay an extra 5 minutes, I would be grateful. If you can't, I understand. But you know, we're already a little behind on the syllabus, so I just want to finish this up here. So let's go ahead and look at example 3. Okay, so I want to mention too here, in the second derivatives test, you have a maximum, a local minimum, a local maximum. That's parts A and B. And part C would be not a local maximum or minimum. Well, what's that mean? I mean, what's that mean? Well, this in Figure 3, they give an example of a sorry, it's called a hyperboloid, right? This hyperboloid, let me see, let me just go back to section 9.6. This is where you learned about some of these different kind of common surfaces. Yeah, that's a hyperbolic paraboloid. You see there the point that's like right there in the middle on Figure 3. It's like like if you look at where the surface goes down, with respect to the y-axis, the surface goes down, and the bottom point there is a minimum with respect to the y-axis. But with respect to the x-axis, the surface is rising. And so the point if you go in the x direction, the highest point there on the x-axis is a maximum, a local maximum. So you can't identify in this Figure 3 if the critical point is a maximum or a minimum. So it's going to be what's called a saddle point. And that's what you have in the second derivatives test. In the second derivatives test for case C, they mention in case C you have a saddle point. Okay, are there any questions so far? All right. Well, then let's just look at a nice example. And we're going to stick to nice examples overall here in this section. Here you have a function. Of course, how nice is nice, right? But here you have a surface, and you locate the critical points by taking the partial derivatives of partial derivative of f with respect to x, and the partial derivative of f with respect to y. And they both need to equal 0, right? And at the critical points. So you can just set then the partial derivatives equal to each other, because at the critical points, both partial derivatives equal 0, and therefore they equal each other at the critical points. And if you do that, you're going to get two equations. You're going to get x cubed. Well, no, hold on. Yeah, all right. So yeah, you're setting the partial derivatives equal to 0. Okay, and then I guess I misspoke here. I mean, it would be okay to do that, but let's not do that. You set both partial derivatives equal to 0. Okay, and you're trying to solve for x and y. But remember, you have two variables, right, that you need to solve for, x and y, and that's why you need these two equations. So yes, you could set the equations equal to each other, but that's I'm not sure that's going to work here. What we can do is from the first equation, we can say y equals x cubed. We can say y equals x cubed, and we can substitute y equals x cubed into the second equation. And if we do that, you're going to get what you see here, what I'm highlighting or blowing up right here. You're going to get 0 equals x to the 9th minus x. And then you can factor that. You can factor out an x, and then x to the 8th power minus 1, you can factor that. And then you can factor the x to the 4th minus 1. And so you get 3 real roots. The solution to this equation is 3 real roots. X equals 0, x equals 1, and x equals -1. And with those values of x, you get some values of y, 0, 1, and -1 respectively. Notice the x to the 4th plus 1, though that would yield on this like highlighted equation, that last factor, x to the 4th plus 1, would only yield imaginary values. And we are interested in real values because the surface is in the real three-dimensional space. So now that you've identified your critical points, here in this example, which is example 3 from section 11.7. Now that you've identified your critical points, you can see if you have maxima or minima there. So you just then, here you compute the second partial derivatives and then you just apply the second derivatives test as they show here. You apply the second derivatives test. It's really just applying the second derivatives test. It really doesn't take that much thought. And again, a lot of programs will find things like maximization is extremely important in math to maximize a surface, maximize a function. So, but the second derivatives test will work very nicely for simple type functions. So it turns out, based on the rules for the test, and again, they're just applying the second derivative test rules. So, like for instance, the value of d at 1, 1 is 128, and the second partial derivative f of with respect to x at 1, 1 is 12. Okay, so since both those values are positive, that's case A, that you have at f of 1, 1 equals -1 is a local minimum. So I think, unless there are any, are there any, and then they similarly evaluate, they show that at -1, -1, you also have a local minimum. And if you look at the surface, here it is, looks like kind of a pair of pants, doesn't it? That's what it reminds me of. At the points 1, 1 and -1, -1, you do have local minima there. You do have local minima, but then there is a saddle point also. There's a saddle point right like in the crotch of the pants, so to speak, in figure 4 here. There's a saddle point, and the second derivatives test identifies that the origin is a saddle point. It's all shown right here. Are there any questions on that? Are there any questions? We're almost done here. Are there any? Okay, how many think this is kind of interesting? Kind of interesting, at least. Or I should say interesting. maybe one person. Okay, thank you, marvelous. Thank you. All right, and final note, they do a contour plot of the surface, okay, in figure 5, and they put values of level curves there, and and you've seen that kind of thing before. So I think that is really really is section 11.7. This is really very representative of section 11.7. I want to keep things simple and applications simple because the second derivative test will work very nicely for sort of your more simple situations. It can get very messy, very ugly if you don't have simple situations. Are there any questions on that? Okay, I'll stop the recording.